This whole thing about the observer is one of the things in physics one of the things I don't like in the popularization of physics, this whole role of the observer. It's a nonsense. I give an example of this. You remember those machines you used to flick and it shot a ball bearing thing up and there was a range of pins sticking out and it went boing, 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 down. And it had you had to get in the win holes, not the lose holes.
Yes.
Now, when you do that, let's assuming it's going to take random trips left and right at each level.
Yes.
Right? We flick the things at the top. We turn the lights out. Where do we expect to be at the bottom? At the bottom, we can draw a thing that's like a normal distribution of where it's going to be. Those are the win holes at the sides, incidentally, which have got the very low probability.
Yes.
And there's a peak in the middle here of where it's most likely to land. Okay, that's the picture. That is the wave equation, if you like, or the probability expectation. We're thinking, I'm doing a parallel here with quantum physics, with what's going to happen here. Okay, now we turn on the light and it happens, and we get a distribution like that if we do it enough times. Now what we're going to do is we're going to do another one, and when it's halfway down, we're going to do a flashlight. Okay, now this one, it's not in the middle when it's halfway down, it happens to be a bit to the left.
Okay.
Now, the light went out again, the flashlight. What's the probability where it's going to be now? Well, it's probably going to be a bit to the left. It's going to be vertically under that, and we've narrowed the distribution now. It hasn't got so far to fall.
New set of probabilities.
So it's got a new set of probabilities. It's got a different shape. It's more peaked.
Yes.
And it's centered off to the left a bit.
Yeah.
Okay. So that's the equation of its probability now.
Mm-hmm.
In quantum physics, we did an observation. Did that alter what the ball was going to do?
No.
No. What it did alter is the probability that we knew now where it was going to be is now different to what it was before.
Because we're looking at it from a different waypoint.
Because we saw it at one point. We got a sneak preview.
Yes.
So the act of observation updated our knowledge of where it's probably going to go.
Yes.
But it didn't alter where it was going to go. It didn't collapse any wave functions. Well, if you by collapsing a wave function you mean it's no longer like that, it's now like that. But it's not mysterious.
But isn't it ironic, Ray, that in quantum physics, because what we're saying appears to be erroneous, we thought we were wrong, but we were mistaken because of our point of view regarding our point of view.
So what I'm trying to show here, and
Yes.
I did the drip model of light with you another time of drips in and out of buckets and what are photons, those things show that there's another way of looking at it where quantum physics isn't the tiniest bit weird. Yes, at times we don't have all the information, and so we have a probability distribution. What happens between those and the next one, there's nothing mysterious. The world is working mechanically. When I say mechanically, I mean waves, right?
Yes.
And so at Newton's time they were horrified by this, because if the world was working mechanically, what place was there for the mind, and what was going to do, and what place was there for God, and all these other things. It doesn't make any difference. If you know the laws of the universe, you know better what's going to happen. How it got there, how do we know? We can make up stories, but we don't know. But if we can work out what's actually going on and understand it from that point of view, that's as far as we can go.
And it doesn't prove or disprove the existence of God. It doesn't prove or disprove that our minds have properties of something. So.
Well, in my view, our mind, I get people talk about free will and determinism, right? And for some reason they think determinism can apply to physical things, but the mind is free. But the mind isn't free. The mind makes decisions based on its existing state, which was a sum of all the existing previous things that happened to you, brought you to the state. At that moment you do something. And there may be a slight feeling of freedom, but what they've discovered by particular pins in people's brains is they actually made the decision a half a second or a second before they thought they did. It was actually going to happen. It was already going to happen before they knew it was.
So it's not always what it seems to be.
No.
And then we look about individuality versus group behavior. The principle of
Yeah.
individuality is described by Duns Scotus. And the fact that, though, we have herd behavior. That's why there's trends and fashion and business ups and downs and cycles of war.
We are all different, and we do all do different things, and it doesn't
But
take
we're all
away
different
from it.
together.
But it doesn't take away from it that our mind, that if our mind is going to do something, it doesn't take away from it that it didn't do something totally random. To me, it would be very sad if people could do totally random things.
And be chaotic.
Yeah, it is pretty much sad, isn't it? Yeah.
It is. It is. But order and chaos are not different things. They're two different stages of the same system.
And we have these things, and you will hear me at times talk about some of the ideas. People in the physics world or the cosmology world will think I'm New Age or something. I'm not. I'm a hard-nosed scientist.
Yes.
But some of the people in the New Age area look at me and say, oh, he's a little bit like us. He can understand us better than those other guys. And they'll tell me things. But some of them I find too flaky. But at times they're very interesting people because I often think that they are the ones that are at the forefront. They're feeling stuff out and it's not clear. And people will often come up with different things. And one will say it and the whole lot will copy it. Whether it's right or wrong, it doesn't matter. I've seen people put stuff on the internet in the early days, in the early 1990s. Someone made something up. As far as I consider, they made it up. It wasn't happening.
Yeah.
But now you can find hundreds of people quoting that and saying it's true and all over the place, and it's not true.
Yes.
It is that the human frequency of the earth is rising, and it's going to cause a new age of man and all of this, because our brains are going to ascend to this new state. The human resonance isn't rising. It can't. It's the speed of light around the earth, you know. It's not rising. It does actually fluctuate slightly with the sunspot cycle and with day and night and things and other things, but it can't keep on rising unless the speed of light was to get faster, and it's not.
No, it's not.
Well, we wouldn't know it was if it was. Well,
but sometimes you have to have contrarians to conventional thought.
Yeah,
and while the
you do,
New Age groups weren't able to back it up with substance, at least they were able to go beyond the show.
Yeah, well, that's what the thing is. One of the things I did when I started putting my harmonic theory stuff on the internet, I posted stuff about physics, I posted stuff about cosmology, I posted stuff about economic cycles, I posted stuff about geological cycles and a few other things, and I started getting email from people in the alternative health field. I really like your work, they'd say. What? And I mentioned it before.
Yeah.
I went to see my friend in Australia, Mountain Man, and he said to me, you've got to apply this to life. And I said to him, no, life's too complicated, I'm only trying to work out the formula for the universe. But he convinced me, and I came home and I applied it to life, and I said, okay, standing waves, when you have a guitar string, it's the length's important, so we'll take this body, take the length of it, and we'll start working it out. And what came out? It tells you exactly where the chakras are going to be.
Yeah, okay.
The strongest harmonics are from 1, 2, 4, 12. 2 gives you the base of the spine.
Yes.
Or the genitals.
Yeah.
4 gives you the heart.
Yes.
And the 12 gives you the other chakras, except the 12th is here, and the 24th, which is the next strong one, gives you this one. So that structure there, harmonic theory says, if we consider ourselves as a standing wave structure, that will give that. Now, here's the interesting thing. The standing waves, there are nervous impulse in the bodies. There are multiple different speeds of nervous impulse, but one of them goes at pretty close to 1 metre per second. And when you start doing that, and taking it going from your head to your feet to standing wave, it takes about, say a man is 1.75 metres tall, it'll take 3.5 seconds to go there and back. That's about the speed we breathe. That wave going around your chest will take a second or a little over to go around your chest. That's about the speed our heart beats. In your brain, it'll go quite a few times faster. About the same speed that the brain waves go.
Indeed.
In the eyeball, if you do one going in the eyeball, it'll give you about the correct frame rate that we can see things at.
So we're finding an interconnectivity, not necessarily when we look at the size or the shape of objects, but when we look at the waves within them.
The dimensions, and you've got to consider what wave velocity. In this case, the wave velocity is much slower than the speed of light, and we'll talk about that separately, about these other cascading effects of the waves at different ones. But so the basic picture I'm trying to give of the universe is there is nothing but either you can think of it either as electromagnetic waves, which make standing waves, which are particles, or you can think of it as vibrations of the ether, which is my preferred form. It's the simplest form. It's just a substance. It's indivisible. It's as fine as you like. So I've gone against Democritus and all the things people have done since, and say it's indivisible. It can go as fine as you like, but you need intense energies to get to the finer scales. So the most intense ones we've made at the moment by banging particles together in accelerators, we can make waves that have got shorter and shorter wavelengths, but only for very short periods of time.
Yeah.
Those ones could exist. So we've got the galactic waves, the stellar waves, the planetary waves, the cell waves, the atomic waves, and the nuclear waves, and then there'll be quark waves. If on a place like the Earth, that's where it stops. But in the middle of the sun, it could be that it goes a little further. In the centre of galaxies, where there's a black holes forming, where there's a very intense energy, it's possible that you might have free quarks. I haven't done the calculations, but I'm saying it's possible, and it may be possible that the next level down is happening in quarks, and that can create energies which are again 30,000 times greater. Just as we go from chemical energies, measured in, say, tens of volts or volts, when you get to the nuclear energies, you're dealing with 30,000 times more. When you bang things together and you start to get to the really quark things, you'll be 30,000 times more again. And those things may be happening naturally, and there can be more levels beyond that. But it depends on where you are, that the energy concentration has to be greater, and it can be much greater. The collapsing of matter to a nuclear state is not the end of the thing. That happens with a
just changes its form.
It's not the last one. That can happen again, but you need to be in the right situation, which would be in the core of the galaxy, and maybe the cores of supergalactic clusters will even go another level. I don't know.
But we're finding the same patterns again and again in all things great and small. Yeah. So you can answer long-standing questions, you can resolve conflicts, and you can find a commonality across things seemingly different when you look at it in terms of waves. Yeah,
and you can unite these things like Nalika finding this, or Lesage finding this gravity. Those all become very clear why they are so, and they must be so. They must be so because of the wave equations of the universe. And a number of the things that do come from the New Age people or the alternative health people and that sort of one, a number of their things, well, we see the chakras, which is an old thing. Yes. We see that actually comes out. And not only that, when you keep going to the next level, it actually gives you the layers at which all the acupuncture points occur. And we can see those. They're inches.
Yes, and they in the joints of our fingers.
In the joints, in our ribs, and in our backbones.
Again, interconnected. And what's interesting?
It's 2 inches, 1 inch. 2 inch, 1 inch.
It truly is amazing, and it never ceases to amaze. What's interesting is that when you try to find answers through waves, your models, the more you look, the more data you add, your models become simpler, not more complex in order to fit the facts.
Yeah, okay, so I mentioned this division of 12 of the height of a person.
Yes.
Which is one of the very strong harmonics.
Yes.
That gives the chakras. I also mentioned that at 1 metre per second, one of the velocities that Earth impulses travel will go to your feet and back in about 3.5 seconds.
Yes.
That it'll hit the 12 division of chakra twice on the way down and twice on the way back, so 24.
Yep.
In 3.5 seconds works out at about 7 or so per second. I mentioned before, I said the Schumann resonance or the brain waves are about 8 cycles per second. Schumann resonance is theoretically actually 7.5 cycles per second. So what we're seeing is the brainwave frequency connected to the planetary vibration, connected to the standing waves down the chakras.
Once again, you're correlating frequency with space and distance.
Yeah, but it's the same wave. We are tuned to the planetary wave in now I mentioned in that other talk about what happens when we're in the presence of waves that are a little faster or a little slower than the Schumann resonance, how it affects our reaction times, make them faster or slower, and result in accidents in that case.
Yes.
So that's all part of that picture. So we can see some connections to perhaps ancient knowledge on these things, as we had in chakras and so on, and acupuncture. And I see other connections. Other people saw them first because they said they liked my stuff and I didn't know what they were talking about. And then as I went into these things, I found there were connections to what some of the people were saying. And so there is genuine knowledge in those areas. There is exploration that feels its way towards future understanding. Sometimes people make some mistakes, I see those. Sometimes they get things right. Gradually they're creeping towards the truth. And I hope this can help it.
I hope it can, because you have found something that provides ever simplified models that explains so many things, answers questions, resolves conflicts, and allows us to take a formula and put it not only to frequency but to distances, and find it as replete and holographic, self-repeating, self-iterating, and that although things seem complex to us a lot of times, it's often because it's merely simple elements happening at the same time.
Yeah. Now, we need to go to that as above, so below type of thing as well. It's interesting because theoretically, the equations in an atom is inverse square for forces. Mm-hmm. Same in the solar system, same in the galaxy. But we see they all look different. At each different scale, we see something slightly different. And the question is, why is that so? And in the harmonics theory, it predicts that there will be major structures about at every 30,000 ratio. They're not fixed. It's not a fixed amount. Mm-hmm. And there's a pattern in it of the primes that come in. There's ratios of 2 between many cycles which have been observed. Many people have observed this from Dewey, and other ones historically did that before him and after him, and continued to do it that weren't aware of those things. And I see in peer-reviewed journals, I see articles published saying, look, there are these harmonic related periods in the sun, and so these things. But so those, that's all going on.
Yeah.
Why is there a difference in this pattern of these ratios in the harmonics theory? Every so often, some different primes pop in. Now, it typically goes 2, 2, 3, 2, 2, 3, 2, 2, 5, 2, 3, or something like that. And every so often there's a 5. Now, it's every time, after every 3, there's usually a ratio of 12 or 24. So those are very important numbers.
Yeah.
And we often find 2 sets of things going on. For example, we'll find the large spiral galaxies at a certain spacing, and at about 1/12 of that, we find the little hanger-on galaxies like the Magellanic Clouds on our galaxy, or the 2 hanger-on ones we see on Andromeda. And I was describing this. Now that's at about 1/12 of distance, so you get another peak there, secondary peak. I was describing that to one guy once, and he said, yes, he says, I've often thought they're H2O molecules. And I went, yeah, there's a big one and 2 little ones. The big one's the O, the 2 H's. They are H2O molecules, aren't they?
How about that?
Yeah. And but so after every ratio of 5 with its surrounding 2s and 3s, we go to a new level. So we go from the scale of the Hubble scale to the scale of galaxies, to the scale of stars, to the scale of planets. But along the way there's these other ratios of 7 and 11 and 13 popping in, and we see, for example, in the solar system we have 2 scales, just like we did with the galaxies. We've got the outer planets at this bigger spacing of about 10 astronomical units, and the inner planets at about 0.35. And it turns out that the ratio there is 14, not 12, because a 7 came in.
Yes.
And those things coming in lead to a slightly different energy balance. That means the solar system behaved differently to what a galaxy did. And in an atom, a different one comes in again. What comes in between the electron and the proton is a ratio of 17. Now 17 is a funny one, because when you have the very common ratios of 12 and 24 combined with a 17, you get, if you make a right angle triangle, the diagonal, a square one, the diagonal there, 17 over 12, or 20, if that's 17, 17, 24, 24 over 17 are both extremely close to the square root of 2.
And that means
on a when you have waves of a rectangular grid, when the ratio 17 occurs, it can lead very closely to making structures that are particularly uniquely stable as a lattice. And that ratio occurs between the electron and the proton. And as a result of that, my study of that, I predicted a new particle at 68 times the mass of an electron, which is 17 times 2 times 2. And the proton is 3 times 3 times 3 times that. So we took up lots of ratios of 2 and 3. And a lot of other particles are various multiples of that one, but it had never been observed. But I predicted it should be there. And just by coincidence, people were in the process of discovering it. And a few months after I made public my prediction, the first reports of that came out, that they had found this particle.
How about that?
Yeah. It's not widely accepted by physicists as an existing particle, even though it's been published about quite a lot.
Yeah.
And the reason is the standard theory didn't predict it. So I had one guy saying, no, that's not a particle, one atomic physicist. He first of all, he said, I'm going to replicate what you did, because he didn't believe that I had predicted it beforehand. But in actual fact, I could prove to him it was in the Usenet groups before. I couldn't find my original post, but I found someone's reply to it and had my thing in there. And he replicated what I'd done. It took him some months, and he produced the maths, and he put in all the existing particles and did the analysis the way I said, to look for things. It's Kotov's method, looking for multiples and fractions of things.
Yep.
And it came up with this figure. And so he was prepared to concede I could have come up with that. He wouldn't concede I did, but potentially I could. And so I got into a discussion with him,
yep,
because he had copied somebody's thing that called me a crackpot, and he had repeated this list. So I said to him, are you a scientist, or are you just a name caller? And he wanted to say he was a scientist. So we went through this exercise, and at the end of it he said, okay, I accept that what you're doing is science. It's just different to what we're doing. He says, I'm not planning to change course. I'm going to keep on this other one, but I can see that you might be onto something. And I'm taking you off that list and accepting that you're a scientist.
Well, that comes. A lot of theories wind up being a little bit ahead of their time.
Yeah.
But we move in cycles too, or we have social change, tides of behavior, and everything like that.
Yeah,
and it seems
sure.
that within our lifetime, right, the resistance to accept different ideas and a different way of thinking are actually being reversed, and people are embracing and even seeking new ways of thinking.
I'm trying to remember the name of the fellow. It won't come to me. There was a guy in the early to middle part of last century who decided the sun's output couldn't be constant. Now, the physicists didn't even entertain the idea that the sun wasn't constant. Why they would do that when they were observing many other variable stars that varied greatly?
Yeah.
Why would you think the sun was constant? You'd have to be a moron. But they were morons, and he set up observatories where you go to places like, is it Arizona? You go up in the mountains or something, and you got very clear air, and he observed the sun there, and he measured its brightness, and he did this regularly, many times, thousands of times.
Yes.
And he found cycles in it, which related to the sunspot cycle and other things.
Yes.
And he had number ones. He was completely ridiculed by scientists all the time. Now they've got spacecraft up there that measure the fluctuations in the solar constant, the solar output, and they plot them all. But he was doing that long before anyone else. He did a lot of hard work to do that, and what did he get? Abuse.
Yes, often the case, the case. But I think the rate at which we're rewriting the books is increasing.
But there's certain ideas that get embedded. When you start building a wall, right, you put one brick wrong at the bottom, it makes a couple of wonks from there on, and you're everlastingly saying that there's this mystery here, but no one wants to rip their wall down to the bottom to start again.
That's true.
When the Greeks had their mathematics and they assumed that all numbers could be represented by fractions, when someone proved the square root of 2 was irrational and couldn't have that done to it, their solution wasn't to fix it up, it was to take them out and drown them.
Well, that proved them right.
Yeah, and then they set about doing it. They didn't want them leaking it. The foundations were wrong. When I was working on harmonics theory, at one stage I had a choice to make, and instead of taking the path that I probably knew was correct. I took the easy way. 2 years later, I realised it wasn't right, the other one was right. I had to throw that away. It's the only thing you've got to throw it away. You've got to go back and go the right path. And you've got to accept, if you can't accept your mistakes, you can't make progress. Or you make progress to a point and get stuck. And I think there's about 4 things in physics and cosmology where they've made a mistake. Things like that variable mass hypothesis and the red shift versus the blue shift of time versus the red shift. That's a fundamental mistake, and it keeps on multiplying.
Because it's in the foundation.
It's in the foundation, and they keep on multiplying it, and they have to have all these other things there to try and patch it up. And again, in the physics, when I mentioned that that photon that left there isn't the photon that arrived there, there's a causality that passes from there in terms of the wave, but the energy there dissipated over the wide area, and this came from wide area. A little bit of it came from there that tipped it over the edge, and that's why
because that thing that absorbed that little bit of energy that got to it was absorbing from elsewhere.
Yeah, and so when you understand that, you know there's not one photon that went from there. That one can cause multiple events or none. It's just the luck of the draw. It's got on average, it's got to cause one. Otherwise, there wouldn't be conservation of energy.
It's a new way of thinking, but it's so ironic that sometimes the path to simplicity can be hard.
Yeah. Well, you have to have that insight, and something has to drive you to that. In my case, the driving thing was I had this harmonics theory, and it predicted these structures, and it predicted atoms, and so and subatomic particles, that they had to be at those scales, and they had to be those type of wave structures, and I knew they had to be non-linear. Those things were absolute, and then I saw, yes, physics has to be non-linear, otherwise we wouldn't see anything. I realised that, and that's my way into the physicist, to say you have to accept that the fundamental equations of the universe are non-linear, otherwise you wouldn't be looking at the universe.
Yeah, we'd pass through it, it would pass through us.
Yeah.
We'd be nothing.
It wouldn't exist.
Yeah.
It can't make anything. Yeah. The next thing I've got to convince them is it's a top-down universe, not a bottom-up.
It was started out big and then got smaller and smaller and
the
smaller.
smaller scales keep falling, yeah.
But we've got this noted here, you're laying it out, you're explaining it.
Yeah.
This is the kind of interview that you would want to listen to time and time again because it's so rich, it's so intense, but it's all connected.
Yeah, well the thing is that this is a background to the other stuff we're going to talk about, because I'm going to keep coming back to this.
Yes.
Particularly when I talk about the harmonics theory, and I'll explain that in much more detail,
Yes.
and why it predicts the structures, and therefore, and why this is different from past theories, that relativity's here, quantum mechanics here, and the harmonics theory there. These are the limits of the universe. We can't observe beyond the black hole. That's the black hole limit. This is the quantum limit. And this is a relationship between energy and one way is energy or mass, the other way is distance. Those are the limits you can't go beyond. And the opposite slopes for those two, they meet at that point, which we were trying to remember the name of, the something or other point. It's
Don't know.
It's a Planck. It's the Planck. Is that the Planck point? I'm not sure. We'll get that right. We'll look it up if I have to.
Yeah.
But we will do that graph, and that will show why harmonics theory is the missing component to explaining that picture. But I don't believe that's the limit, the finish. You've got these 3 things. They are all manifestations of one thing, which is the wave equations of the ether, which are very close to Maxwell's equations. There needs to be a tiny tinkering to realise that that is non-linear, and then you can probably throw away a couple of the equations that you won't need anymore. It's interesting that the operators used in Maxwell's equations, which are just this thing about overshooting and the momentum and the wanting to return to the original state, but the operators that they use in those, one of them is the electric field, one is the magnetic field. The magnetic field one, the operator used is called rot, which means rotate. And the other one the operator uses is, there's a number of them. They're vector operators. And that rotate one means, what it's saying is, the magnetic field is the local rate of rotation of the ether. That's what it is. When you examine the equation and see what it's doing, it's measuring the local rate of rotation of the ether. That's what the magnetic field is. And the electric field is the local rate of acceleration of the ether. That's all they are. So you can think of them as electric field and magnetic field and the things, but what's actually happening when you get that light doing that little wiggly thing that I said down there through that medium, it causes an acceleration and it causes a rotation because the thing goes like this and like this, and that's the magnetic field is fluctuating from one to the other as it goes along. And it's accelerating by moving back and forwards. So that's why there's an electric and magnetic field moving that light is, because that's what Maxwell understood. He was he was looking at electricity and magnetism. He was working out, because they knew they made coils, and if they moved things relative to them, things happened. And so they had all this stuff, and some of the other guys before him had worked out quite a lot, and he finally put it together to say, these equations work, and that's what he was doing, the equations of an ether.
Indeed, indeed. And again, waves bring us to the answer.
Waves, yeah.
We have to think differently about matter. I mean, we know that matter itself is more than 99.99% space.
It's 100% space.
Yes.
It's just the waving of the space.
Yes.
One of the things people talk about is the interconnectedness of things.
Yeah.
And so I think it's worth doing that. We start with the atom. We'll start with atomic particle. Atomic particle, I said is this, an outgoing wave and an incoming wave, which interact to make a standing wave. So around the particle are these parts that are wobbling opposite ways, continually all around. And when you start to look at that, it's easy if you do it this way, but when you get to the pole, something different has to happen, and it turns out it does this sort of weird loopy thing, which I'm not going to try and do with my hands, but you can look it up in the standard physics books. It was explained as, it's called spherical rotation. It's different from normal, what they call cylindrical rotation. And to get the effect, what you imagine is the room's full of the jelly or jello. We've got a little sphere of it here. We're going to put a thing in here that's a pole. We're going to rotate this by 180 degrees. So we've now distorted this, so the part that used to come to there now goes down to here, and the part that used to go there goes up to there, right? So it's all distorted like that around. And now what we're going to do is rotate this pole around. And you think, this is going to rip the jelly for sure. It doesn't. What happens is, these things go around, and they come back to where they started, and it takes 2 rotations to get back to where it started. The first time, what happens is, the ones that are going out to the side go over, and they go under, and they go over, and they go under. And the whole thing never rips. And this model is in the physics textbooks as an example of why the electron has a spin half. Right? Milo Wolf says that is the wave, that is the equation for the electron.
Indeed.
And so it's that's what's going on now. Those waves going out from the electron, where do they go to? The answer is, at some point, they become the incoming wave of another electron. Now, a little bit of it does, because it's spreading out all over, and there's another electron there. A little bit of that becomes incoming wave of that, a little bit of another one. Some of them are, in the object they're in, are going very quickly going into other ones. But some of that's escaping out and going far beyond the Earth. Some of it's becoming the incoming waves of electrons on the far side of the universe. It takes billions of years to do that, or more. So that's happening. Does that explain some strange things about the universe? They had this thing that was called the large numbers hypothesis. And 2 guys, Dirac and Eddington, who were both famous physicists. Dirac got a Nobel Prize. I'm not sure Eddington did, but he did some very clever stuff. The thing they got to was that there was these couple of numbers, 10 to the power of 40, which I mentioned before about gravity, and 10 to the power of 80, popped up a few times. The first time one popped up was 10 to the 40 is about the ratio of the strength of gravity compared to the charge force in a hydrogen atom, right? So the gravity is 10 to the 40 weaker than the charge force. The other way it popped up was, now they did it in terms of time. I'm going to give you the correct way, because it's the same thing, but I think it's more sensible. The size of the observable universe versus the size of the atomic particle is about 10 to the 40 ratio as well. The other thing is there's about 10 to the 80 particles in the observable universe. So we've got these three things.
Yes.
On the face of it, it'd be an amazing coincidence if they weren't related somehow.
Yes.
Okay, let's take this model
Yep.
of the waves in the ether, the outgoing waves of the particles. As this wave goes out across the universe, when it's travelled a distance that is 10 to the 40 times the size of its wave, it's spread out over a sphere, the area of which is 10 to the 80 times the area of the particle. Right? It's a square.
Okay.
The surface of a sphere goes up as a square of the radius.
Yes.
That means if there were 10 to the 80 particles in that space, it would have hit the inner wave of all those other ones and been absorbed or gone in and come out again as part of that particle, right? So it makes sense that within a distance of 10 to the 40, there would be 10 to the distance of the size of the wave, there would be 10 to the 80 particles, because that's exactly how many you need for it to become the incoming wave for them. If there'd been more in there, then that would have happened sooner, and we're talking about a smaller number than 10 to the 40, right?
Yes.
That's the thing, and that relates to gravity as well, because we said that before.
Yeah.
That's the rate at which the blue shifting is occurring.
Yeah.
So those are all tied together by this. That's another one of these things that sits on its own as a little interesting quirk that no one had worked out, which is explained by this way of looking at it as fitting in to the wave structure of the universe, that the outgoing waves hit other ones after that amount of time to go in there.
It's becoming conceivable, and some of the things you touched on have been written about in articles that are hard to understand. Some of the things you talked about have been written as conflicts and questions, of course the most classic of which is a light, a wave, or a particle, and also supporting how time and space are actually the same thing. But what about string theory? They're saying it all reduces down to possibly a small handful.
They're trying to have
of
little
formulas.
vibrating things.
Yes.
That's what I said. They were trying to work from the bottom up. They're doing it the wrong way. The vibrations start from the top and work down.
Okay.
Incidentally, string theory has not produced any new predictions of anything that can be verified, right?
Okay.
Zero. Harmonics theory has at least 14 predictions that it's made that have been tested. Sometimes they were explanations after the event of things that were known but no explanation was for, and sometimes they were new predictions like a new atomic particle and other things that were subsequently discovered and proved that it was working. So it's a way ahead there. String theory, two of the leading guys in string theory a few years ago both said the same thing at the same time. I think they both wrote books saying it was fun, but we're throwing it away.
Good.
It doesn't lead anywhere.
Well, yes, and there's many times that has happened, as you pointed out.